Welcome everyone. It's my pleasure to welcome you to this first talk for the new semester for the Spectral Geometry and the Cloud seminar. This is the 124th talk since we started, and we keep counting. And today I have the pleasure of introducing Cyril Letrouit, who will speak about maximal multiplicity of Laplacian eigenvalues in negatively curved surfaces. Cyril, the stage is yours.
Okay, thank you very much for the invitation. I'm very pleased to speak at this seminar. So what I will present is joint work with Simon Machado, who was in Princeton and now in Zurich. The setting I will be talking about today is a usual one in spectral theory. It's you take M to be a closed, meaning compact without boundary, connected surface, endowed with a metric H. And so I insist already on the fact that I'm dealing only with surfaces for a reason that I will explain later. Then, of course, you have the Laplace-Beltrami operator that is denoted by delta, and the eigenvalues of minus delta are repeated according to multiplicity and written as I've written here. So lambda 1, the convention I take is that lambda 1 is 0, then lambda 2 is strictly greater than 0 because the surface is connected, and then you have only you have lambda 3 greater or equal to lambda 2, etc., tending to plus infinity. So the question we ask is the one of multiplicity, and typically for a typical surface, I mean lambda 2 or more generally lambda j has multiplicity 1. But the question I will ask is how large can the multiplicity be? Meaning, for example, if the surface is very has a lot of structure, has a lot of symmetries, then the multiplicity can be larger than 1. It turns out that the multiplicity may be bounded above in terms of the genus of M. And this is a bit surprising at first sight because the genus is topological and doesn't see the metric. It means you will have some bounds which are only depending on the genus and not on any information on the metric. So to start, I will present elementary cases. So meaning, for example, the sphere, the torus. So consider simple topological surfaces. And what we are allowed to do is to vary the metric. And the goal is to maximize the multiplicity of lambda 2 or of lambda j. For example, if you take the sphere, so the topological sphere, meaning you don't have the canonical metric, but any metric on it, in any case, the maximal multiplicity of lambda 2 you can get is 3. And this is a result due to Cheng in 1976. For the torus, if you take the topological torus T2, the maximal multiplicity is 6. It's due to Besson in 1980. For the real projective plane, it's 5, also due to Besson. And for the Klein bottle, it's also 5, Colin de Verdi and Magirashvili. And in all cases, these are optimal bounds, meaning there are some metrics which achieve these bounds. So more generally, what I want to do is to take general surfaces and to try to find bounds which work and which depend, for example, only on the genus. So I introduce two notations. So first, mj of M is the maximal multiplicity of lambda j where the maximum is taken over all metrics H on M. And mj of mh, it's when you fix the metric, it's just the multiplicity of lambda j. So the main quantity I will be dealing with is the first one. So the very first result was obtained by Cheng in 1976. And it was mj of M has an upper bound like half of 2g plus j plus 1. What it means, it's quadratic in the genus, and in all the talk I would be thinking about high genus, so and especially g tending to plus infinity, and so it's quadratic in the genus and it's not sharp. Besson improved the bound to something linear in the genus, which depends on the orientability or not, but linear for g plus 2j. Then Sevnek in 2002 improved by a factor of 2 the bound for lambda 2. And finally, and this is how I got interested in the subject, is because Maxime Fortier-Bourque and Bram Petri, they considered the case where you know that the metric is hyperbolic. MH is a hyperbolic surface of sufficiently large genus. Then you can prove that the multiplicity is at most 2G minus 1, so it's slightly better. But the proofs are very different and very nice. So, and then there have been some sublinear bounds, but under strong assumptions. And indeed, there are some conjectures that I will make precise later. So the sublinear bounds, the ones I'm aware of, are by Gilmore, Lemasson, Salsten, and Thomas, 2019, for hyperbolic surfaces only. And the one by Monk that I will present now, 2020. So it's sublinear, meaning it's little o of G when G tends to infinity. And it holds under the several conditions. So the precise statement is there exists C greater than 0, such that for any large enough G, which is the genus, of course, any J in N and any hyperbolic surface in some set that I will explain later in a minute, you have MJ. So the multiplicity of lambda J is at most a constant. Somehow it doesn't care that there is square root here, but G over root log G. So it's better than just G. And the point is that this set, besides being restricted to hyperbolic surfaces, is also restricted to surfaces which converge in the sense of Benjamin Ishram toward the hyperbolic plane. So it's a very nice result, but in a particular branch of spectral theory of hyperbolic surfaces, considering the limit where somehow most points have a quite large injectivity radius, meaning there are few short loops, few short geodesics. But there have been many talks in this seminar about this subject. The goal of the talk and the goal of our work is to derive a sublinear bound on the multiplicity, which is valid under much less restrictive assumptions, and which indeed is valid as soon as MH is negatively curved. And then, this is the first goal. The second goal is that we will see that this sublinear bound works not only for the multiplicity, but also for what we call approximate multiplicity. And it's just a very classical problem. It's to bound the number of eigenvalues in small spectral windows. And in fact, they are pretty small, the ones we consider, but it's better than just bounding the multiplicity. It means you are able to say that there are not more eigenvalues than this in this spectral window. And finally, although our bounds on the multiplicity, on the exact multiplicity, are not sharp, I mean, we are not able to prove it at least, the bound on approximate multiplicity is sharp. And it will show that these bounds with G over log G or something like this are indeed the right bounds if we are considering approximate multiplicity. And I finished the introduction by mentioning what is the starting point of our work. How did we come up with this idea of doing this problem? It's because I knew by discussing with Yufei Zhao that there was a paper called Equiangular Lines with a Fixed Angle by these authors in 2021, which was proving a spectral result on graphs which had this flavor. And in fact, it's somehow the analog result for graphs. Let me explain a little bit more. So in this title, there is equiangular. So let me recall what it means. It means the following: a set of lines passing through the origin in Rn is called equiangular if they are pairwise, if all the lines are pairwise separated by the same angle. Okay, you have many lines. If you take two of them, it's also always the same angle. And the problem is to determine the maximum number of equiangular lines that you can put in a given dimension. They are all through the origin. Okay, I think it's clear. And in fact, there is a reformulation of this problem in terms of maximal multiplicity of the adjacency matrix of graphs of bounded degree. And when I say graphs, I mean combinatorial graphs, not quantum graphs. So the precise statement that I call key ingredient in this paper, you will see it's very it's exactly the same kind of results in the graph setting. So for every j, which is the index of the eigenvalue, and every d, there is a constant depending on d and j, so that the quantity Cn over log n is an upper bound for the multiplicity of the jth eigenvalue of the adjacency matrix of every connected graph with n vertices and maximum degree at most d. So to put it differently, you take a graph with n and large n vertices. The degree of each vertex is at most d. You look at the jth eigenvalue of the adjacency matrix, and you know that the maximal multiplicity is at most Cn over log n. And of course, there are n eigenvalues. So it doesn't seem very impressive to have n over log n, but in fact, it's already a big thing. And so this is the starting point for the motivations. So of course, for surfaces, for graphs, the motivation of the spectral problem is the equiangular problem. For surfaces, looking at these questions, in fact, the bounds on multiplicity gives you some information. For example, there are some papers in the arithmetic community about multiplicity on arithmetic surfaces. There is also, but I don't know how it works, but apparently there is also a link with quantum chaos that if you know sufficiently good bounds on multiplicity, you can say something about quantum chaos. Probably some people in the audience know that, but I don't know. And so the second motivation is that, in fact, there is a whole business of transferring results from graphs to surfaces. And somehow with this paper, we improve the technology in part of this business. And finally, we would like, I will not do it in the talk, but to explore the connections with other questions on the bottom of the spectrum. Of course, it's not high frequency what I'm doing, it's bottom of the spectrum. And the very classical question many people are working on at the moment is the optimal spectral gap. And here it's different, it's multiplicity, but there are some connections, clear connections that you will see.
May I ask a question, please?
Yeah. Yeah.
You speak about the eigenvalues of the adjacency matrix. What happens if you speak about the Laplacian of this graph?
Yeah, so for the adjacency matrix, so the result is working for any graph, even irregular graph. If you specialize to regular graphs, so adjacency matrix is equivalent to the Laplacian, then the bounds are slightly better, meaning it has been proved a little bit after that you have, instead of Cn over log n, you can do Cn over log n to the alpha for some alpha. It's slightly better. It's a result due to Mackenzie, Rasmussen, and Srivastava. Okay, so that's the end of the introduction. Now I'm going to the statement of the results. So for that, so the bounds I will present are for negatively curved surfaces, but if you want a uniform constant, somehow you have to specialize to restrict a little bit your set. In the end, you will exhaust all negatively curved surfaces, but if you want some uniformity, you have to restrict to some class. So let me do it in this way. So first, I introduce a set T, which is a set of triple of reals. So T is the set of AB rho, such that B is lower or equal to A, strictly lower than 0, and rho is strictly greater than 0. And what do they serve for? See, if you have a G, which will be the genus greater or equal to 2, and AB rho something in P, we denote by MG AB rho the set of closed connected surfaces of genus G, and with Gaussian curvature kappa, satisfying that kappa is everywhere between B and A, so the Gaussian curvature is negative everywhere, and the injectivity radius greater or equal to rho everywhere. Okay, so the bounds will be uniform in this class. And of course, if you take B and A to be very close to each other, it's less interesting than if you take B to be very negative and A to be very close to 0. Okay, and rho, you should imagine it to be very small also. So for example, if you take A is equal to B is equal to -1, you get all hyperbolic surfaces with injectivity radius greater or equal to rho. And I just remind you, because it's very important for the mental picture, that surfaces with large genus G have large area in this setting, which is of order G actually, because we assume that kappa is between B and A, And there is, of course, the Gauss-Bonnet theorem, which then implies that they have large area. So you should think of large things. So there are two results somehow. This slide is the first one. Next slide is the second one. And they are the second one is the converse of the first one somehow. So this is the main result. So for any triple AB row, for any index J, which will be the one of the eigenvalue, any K1, K2 greater than 0, there exists a constant, and you see that it's uniform once you've fixed AB row, such that for any genus G, and any surface in this set where you have the right bound, number of Laplacian eigenvalues in this window, and in particular the multiplicity of lambda J, is at most C G over log G. So this is a sublinear bound, and it's not only for multiplicity, but for approximate multiplicity, because you see you have some, it's an interval, it's not only just lambda J. So K1 and K2, you can take them as you want. So it's interesting to take K1 to be large and K2 to be small a priori, because then the number of Laplacian eigenvalues in this big interval will be nevertheless bounded by Cg over log G. Of course, this seems to be quite weak because it's just log G gain, but I will explain in the next slide that this is sharp for the approximate multiplicity problem. There is a second version, slightly stronger, if you assume a spectral gap on the surface. So it's exactly the same statement, except that I put in red the differences. So you have this triple, this index, this constant, you add delta, which will be the spectral gap. Then there exists C and alpha, such that for any G, any surface in this set, with which you assume moreover that there is a spectral gap lambda 2 greater or equal to delta, then the number of eigenvalues in the same interval is at most, instead of Cg over log G, you have Cg over log to the alpha, log G to the alpha. Okay, so slightly better. So as I said, what is interesting in these bounds, it's that they are sharp in some sense, because otherwise it will be again something, just a bound that we don't know how to do better. But here, so first, yeah, I comment. So what we are happy with this result somehow because it's different from previous ones, because there is no hyperbolicity or Benjamin-Schramm convergence. It has to rely on different techniques. Converse theorem is to show the sharpness of the approximate multiplicity bound. So it's just a construction of hyperbolic surfaces with high approximate multiplicity. And here I say hyperbolic surfaces because you don't have to take varying curvature surfaces to have high multiplicity. You just take hyperbolic ones. So the result is there exists C and K and a family of close connected hyperbolic surfaces, Mn Hn of genus tending to infinity, such that for any n, there are at least this large number, so nearly G, but G over log G to the 3/2 eigenvalues in this interval, which is somehow you took K2 to be 1/2 here in this example, but it's quite a large set. So you see, it's not exactly the proof, it doesn't prove exactly sharpness, but it's not far. And for this result, because it's my only slide on this converse theorem, I just mentioned here how in two lines the proof works, because it's interesting, how do you construct surfaces with high multiplicity or high approximate multiplicity? So the quick tip is the following. The first step is first to construct graphs which have high eigenvalue multiplicity. And it's been done by the paper I mentioned to Uzi Smilanski, by Mackenzie, Rasmussen, and Srivastava. They've done, in fact, constructions where using bipartite Ramanujan graphs, which are known to exist since the mid-2010. These bounds are somehow exactly, you see, if you have n vertices in the graph, they tell you that you have multiplicity n over log to the 3/2 of n. So it's exactly the same bound for graphs. And then there is a very nice branch in the literature of the 80s, which explained, it was due to Colin de Verdi and Colbois, how to turn these graphs into hyperbolic surfaces and it's in fact quite general. You can turn graphs into hyperbolic surfaces by gluing hyperbolic pairs of ends according to the structure of the graph. So you look at one vertex and you try to reproduce the half edges which go out from this vertex. So you take pens with constant -1 curvature, and you glue them. For example, here in this line, you would glue them, and here, this hyperbolic surface with boundary is representing one vertex. Okay, and you have as many half edges as connected components of the boundary. And then you glue again the vertices together according to what you see in your graph. And in the end, you have a hyperbolic surface. The question is how to relate the spectrum of the two objects. And this is a theory which has been developed by Colin de Verdi mainly about stability of eigenvalues when you are turning graphs into surfaces. That's the end of this converse theorem. Just some comments now. So why am I only speaking about surfaces and not higher dimensional manifolds M? It's because Eve proved in 1987 that for any closed connected manifold of dimension at least 3, in fact, any finite sequence like this, the beginning of the spectrum of minus the Laplacian, if you choose well the metric on M. So M is fixed, it's any manifold of dimension at least 3, but you can choose the metric and you can realize any sequence. In particular, if you decide to take lambda 2 up to lambda n or very large n be equal, you know that it's the spectrum of some metric, of some Laplace-Beltrami operator. So you know that the multiplicity cannot be bounded when you're in dimension at least 3, just in terms of the manifold. You have to know the metric.
Hi, Cyril.
Yes.
So you can ask about hyperbolic 3 manifolds.
Yes, and I don't know. If
Okay.
you specialize to this, I'm not sure. And I cannot say that I know very well this paper of Eve, so.
Okay.
But for sure, in this paper, it's obtained by degenerating and exploding the metric, so it's not hyperbolic. Eve can correct me, but I'm pretty sure it's not hyperbolic in this construction at least.
But does your method, does your method make sense for hyperbolic 3 manifolds?
No, I don't think so. No, I
Yes,
have to think.
I can add some comment. In fact, the metric I was constructing are not the curvature is not pinch. It means that the result by Cyril and co-author could be extended to higher dimension because there is no curvature condition. My example are very wild metrics, which are not at all negative curve. So
Okay, maybe.
it's not clear for me that you cannot extend to
Okay.
higher dimension with a pinching condition. It's not, I don't know.
Okay.
I don't remember, in fact, exactly how to control the curvature in my examples. Okay, just.
Okay, thank you, Yves. Okay, so now the second comment is about the method used in the proof, because it's difficult to imagine how to bound the multiplicity. So the first methods were, of the first papers by Cheng and Besson, was to consider nodal sets of eigenfunctions. And the idea is the following. If you have a multiplicity which has a large eigenvalue, you have very large eigenspace. And so by taking linear combinations of the eigenfunctions within the eigenspace, you can find an eigenfunction which will have a high order of vanishing at some place. And in fact, Cheng observed that it's possible to find an upper bound for the order of vanishing just in terms of topological information. And so in terms of genus somehow. And this is how it works roughly. I'm not an expert either, but this is the rough idea. Then there the papers with the sublinear bounds with for hyperbolic surfaces, they were done by analyzing the Selberg trace formula or the Selberg transform. And these two different papers, they have either Selberg trace formula or Selberg transform. But in any case, the Selberg trace formula is an equality between the spectrum and the closed, the length of the closed geodesics on the surface. And you can turn it into inequalities, but when you choose appropriately the test function, you can turn it to inequalities, which give you some information about the multiplicity. And this is also the idea used by Fortier, Bourque, and Petri. And our method is completely different. So first, we use the geometric idea that was coming from this graph paper to introduce what is called an R-net, and I will explain what it means. And then we have to be clever with heat kernel estimates to find out how to make it work. But in a word, it's also a trace method, which we are using, except with the heat kernel, but alone it wouldn't work. I mean, it's not sufficient to just have trace method. The main input is to have this geometric idea of introducing an R-net. So I will insist on it. And let me finally mention the Colin de Verdi conjecture, which is from 1986, because Yves conjectured that, in fact, you can find a closed formula for M2 of M, which I recall you is the maximal multiplicity of lambda 2 that you can achieve for one metric, H particular metric on M. Okay, you can. This is a maximum multiplicity on M. And the conjecture is that it's equal to the chromatic number of M minus 1. And the chromatic number is, again, a topological information, which is defined as the largest N, such that the complete graph with N vertices, N, embeds in M. So, for example, for the sphere, it's 4. And so M2 of M is 3, and that's correct. We saw this during the second slide about elementary cases. There is a general formula, in fact, for the chromatic number, which was derived in 1968 by Ringel and Hughes. It's equal to this complicated expression, but here you have what you should see. There is the Euler characteristic here. And this formula is not working for K2, and this is the only exception, K2, the Klein bottle. So the Euler characteristic, it's related to the genus by these formulas in the orientable and non-orientable case. And so if you put this formula, you get that roughly the chromatic number is roughly root B. So the maximal multiplicity is roughly root G. This is the conjecture. And so I recall you that our actual bounds are just slightly sublinear. So we are very far from it. But the conjecture is verified for elementary cases, meaning for all the cases I presented, the sphere, the torus, the Klein bottle, and the projective plane. And it's supported, this conjecture, by lower bounds, not by upper bounds. As I said, and upper bounds are somehow more complicated to obtain, but lower bounds, it's already something. So two lower bounds. First, Logcq and Colin de Verdi give examples for arbitrarily large V, where M2 of M is greater or equal to some expression which has the order of root V. Okay. And the strategy is again to turn a graph into hyperbolic surfaces. And here they take the complete graph for which you know that the first non-trivial eigenvalue has multiplicity n-1. The genus roughly, it's something like n square. When you have the complete graph, you have like n square poles. And so you see that the multiplicity is roughly root of the genus. Okay, and then it's even better if you allow yourself to consider not only the Laplace-Beltrami operator, but also Schrödinger operators. So Colin de Verdi, Yves gave examples for arbitrarily large G of Schrödinger operators, which have the first eigenvalue equal to 0, which the multiplicity of lambda 2 is exactly equal to the chromatic number -1. Okay, so this is not an upper bound, this is just an explicit construction of a Schrödinger operator. Nice conjecture, but our work will not tell you how to prove it. Although we are happy because, as I said, we are working with an idea coming from graphs, and you see that this conjecture is about embedding graphs. So it's not absurd, but we tried to combine it and we didn't manage to. So we didn't prove the conjecture with our tools. So now I'm turning to the proof, and the proof has 5 main steps. And so I will try to not to lose you. So remember, it's based on trace method, and it's based on the heat kernel and on R nets. So first slide is about heat kernel, and just I'm going to prove the theorem in a simpler form, which is the following: for any AB rho, so AB the bounds on curvature and rho on the injectivity radius, there exists C such that for any genus and any surface in this set where you have the right bounds, the multiplicity of lambda 2 is at most CG over log G. So the difference is I'm focusing on lambda 2 and not lambda J, and I am not working for approximate multiplicity, but just for exact multiplicity. And in the end, I will explain that there is no difference. In all the scale, all the parameters are fixed and the surface is fixed. First idea, it's that since in the graph setting, they are working with walks on the graph. So it's natural to consider, instead of just minus delta, to consider the heat kernel, and at time 1, in fact, e to the delta. The eigenvalues of e to the delta are denoted by mu I, which is equal to e to the minus lambda I. And so mu1 is 1 because lambda 1 is 0, then mu2, etc., tending to 0. So for the rest of the talk, we forget about the lambda i's. We are just dealing with the mu i's. And of course, the multiplicities are preserved, which is good for our problem. So now the heat kernel, what are we doing with this? So the geometric idea is the following. And I see that, the slide is a bit cut, but it's my fault. So the idea is the following. We fix a small constant, small meaning independent of G, and in fact, it's something which you need to have, but it's technical, so I don't tell you how to fix it. And we set R1, which is T times log G. And R1 net, the set of points, x1 to xl in the surface. So I draw a picture here, which corresponds to the idea, is that for any x, there exists an index between 1 and L, for which the distance from x to xk at most R1. So the xi's are points which are well distributed in your surface, in the sense that no region of size size or diameter or something like R1, no region contains no point xi. Every region contains a point. So, for example, this point x is not too far from x2 and x3, for example, and not too far from x2, let's say.
And Cyril, you don't assume that the set x1 to xl is small? You don't assume that the distance between the points?
Yes, I will assume this. Yeah, exactly. I will say in just now that in fact you can assume, if this was your question otherwise, that you can take L to be not large. You can take L to be at most CG over log G. So of course, G is somehow the area of the surface, and over log G is because there is, this is the parameter we took. Of course, you should imagine R1 is also something large, because it's G is going to infinity, so it's something large, but it's much smaller than the typical diameter of the surface, which is log G, or constant time log G for a typical surface. Okay, I don't tell what it means, but it's large. And for example, okay, let me tell you how you prove this, because in fact, ball of radius R1 has volume. You can prove it has volume at least C naught log G for some C naught. And this is because you have an assumption on the injectivity radius here. Otherwise, you couldn't prove this. If your surface is too thin, it can be, by the Collar lemma, it will be very long also. And so if you want to have points which are, no region is left empty, you will have to have too many points. So you have, with this is why also we do these assumptions. And okay, I'm sorry, the slide is cut, but I'm saying that if the spectral gap if we assume the spectral gap as a condition, that you have a spectral gap and you know how much, the balls this time have volume, exponential volume in R1. And so in fact, the bound will be better. It will be Cg over log G to the alpha, because the balls are bigger. So each point covers a bigger portion of the surface. So you need less points. Okay, I hope it's clear. So you have certain number of points, and this number is in fact exactly, this number which will tell you this bound of G over log G in the end about the spectrum. This is why we have this bound. So still about the RNet, we round each point, x1, x2, etc. We just consider the ball of radius 1, in which we call it Vi. Okay. So for any k, we pick small ball Vk around xk. No, it's not of radius 1, it's of volume 1. Sorry. And the whole idea of the proof is the following: for any x, quantitative fraction of the mass of the heat kernel at time R1, for any x at time R1, the heat kernel has some portion of the mass contained in one of the VKs. Of course, because the heat kernel, for example, in hyperbolic surfaces, the heat is concentrated at distance R1 somehow of x, exactly, not root R1 as in the Euclidean case, but R1. And there is, of course, it's not exactly true. There are some things which are not uniform within the ball. You have to deal with remainders, but somehow it's this idea that you are controlling the heat kernel everywhere. Now we introduce an orthogonal projection, which will have very important role. It's the orthogonal projection from L2 of M to L2 of M with the volume induced by the metric. Orthogonal projection to the functions which are orthogonal to all characteristic functions of the VK. So here you project and you try to have average 0 over the VKs. And in particular, the rank, the codimension of P is L. Okay, you have L conditions. L is the number of points in your net. It's not too large. So that's the end of the RNet section. And now the idea is to relate the eigenvalues of A, which is here, is just e to the R1 delta, so the heat operator at time R1, with the eigenvalues of P to the R1 delta. So it's beautiful because you have a link between the eigenvalues of two operators when you put projections, and it's called Cauchy interlacing because the eigenvalues are interlaced. So the statement is the following: let A be a compact self-adjoint operator on a Hilbert space H, and this will be the heat operator. Let P be the orthogonal projection, but in our case, it will be the one we just defined, onto a subspace of H of the dimension L. We denote by alpha I the eigenvalues of A, by beta I the eigenvalues of B equal to KP, and then for any J, you have alpha J greater or equal to beta J greater or equal to alpha J plus L. And in fact, it's very easy to prove. It's just min-max. And the thing is that if you have a multiplicity in the eigenvalue, if you have alpha J, which has a lot of multiplicity, then all the beta J's will be also equal in between, because you have alpha J, for example, equal to alpha J plus L, so all beta J's in between will be equal. So if you have eigenvalue multiplicity for A, you have multiplicity for B. So the application, as I said, A is this, H is just the L2, B is P, A, P, and we set M to be the multiplicity. We are considering e to the R1 delta. So the eigenvalue, the corresponding eigenvalue is mu2 to the R1. Of course, it's mu2 because e to the delta, and to the R1 because to the R1. Okay. In prime, we denote it's the multiplicity of mu2 to the R1 in this operator as an eigenvalue of this operator, but possibly it's 0. Possibly it's 0, but it would be favorable if it's 0, because in fact this theorem tells you that M is bounded above by M prime. This is exactly the application plus the codimension of P, so the rank of identity minus P, which we know is bounded above by Cg over log G. Now, since our goal is to bound the multiplicity of mu2, we just want to bound M, and this bound tells you that you just have to bound M prime. You have to understand multiplicity in this operator. And you can forget about this G over log G because our bound is of this order. So this is a nice lemma that is independent of our work. Of course, it's very simple, but it's beautiful. I didn't knew it before. Now the trace method that we are using, like many people in spectral theory, recall that R1, the parameter of our RNet, is C log G. And now we take a second parameter, a different scale, which is C log G. And we call it R2, and C is the same constant. And N is just the quotient, and we take the integral part of this. So the trace method, for which operator? It means we consider the trace of P to the R1 delta P, somehow the heat kernel at time R1, and we put it to some power, 2 to the R2 over R1. So in the end, all this operator is somehow related to the heat kernel at time 2R2, somehow. But you have projections, it's more complicated. And as always in these trace methods, you express the trace in two ways. On one side, you have the eigenvalues. So here, of course, you know that in this operator, by definition of M prime, you will have mu2 to the R1, which is an eigenvalue of this, repeated M prime times. You have a trivial lower bound here. And then on the right-hand side, you can express it as an integral over the manifold. And here delta x is just the Dirac mass on x, which is a point varying in M. So now, you see, we want an upper bound on M prime, so we just need an upper bound on the right-hand side. And we will prove that for a large proportion of x, we have a good bound. And what is nice about this bound is that you have, again, this expression of mu2 to some power, which will turn out to be exactly the same, and so it will cancel in the end, times a constant, or a constant depending on the genus, but it would be very bad if it were 1. It's just below 1. It's just better than 1, but it's crucial in the proof. Otherwise, you wouldn't get anything. And this gain is everything. This epsilon of G gain. Epsilon of G is actually something like the exponential of minus CR1. So something small, but good enough so that when you put it to the power n, you really gain something. Somehow, you have a gain when you are at time R1, and now you exponentiate it with time R2, and you get a bigger gain. And how to finish the proof once you have this? You combine 1 and 2, you just plug in, you use the expression for the volume, okay, the volume of M, because this bound, you don't see X anymore. So the integral is trivial. And using that the volume is related by Gauss-Bonnet and our bounds on curvature that we've fixed, you get, it's like G. So M prime, you simplify by mu2, you simplify the eigenvalues, you get G, 1 minus epsilon G to the 2n. And 1 minus epsilon G to the 2n gives you a denominator, which is in fact much better than 1 over log G, but let's say we just put this rough bound because we knew that we had, in any case, a remainder term for M, which was... So in the end, this is the bound for M prime, and this concludes the proof if you know how to prove, but who is the main thing. So first few remarks before going to the proof of 2. The assumption on the injectivity radius that we are using, that it's bounded below by rho, even if rho is very small, we need it, is used to construct an R1 net, as I said, with at most CG over R1 elements. Otherwise, it's not possible. And also in the proof of the gain, that I will explain quickly, not quickly, but in a second. The bounds on the curvature, you've seen we have already used them in the estimates for the heat kernel when using Gauss-Bonnet, etc. And what I have not explained at the moment is that what are the... Okay, there are some we took inspiration from the graph paper I was mentioning at the beginning, but in fact, it's much more complicated. And one of the main reasons is that in the graph case, you are considering just walks where you jump of one step at each time. And so there is finite speed of propagation in the graph. Whereas in our case, we are forced somehow to work with the heat kernel because this is what is understood best for surfaces. And so infinite speed, it's a bit mixing everything. So you have to introduce cutoffs to recover locality and to control your remainders. Now, let me explain, because this is the core of the proof, I have to explain this to you, how you gain something by introducing these projections. At the moment, you didn't see why I introduced a projection, an RNet, doesn't seem useful. For a large the lemma that we will prove is that for a large proportion of X, there holds this estimate, which is exactly the number 2 that I mentioned before. For some gain, which is sufficiently large, even if it's still small, it's sufficiently large. How does it work? So this slide is just preliminary to the real idea. First, as I said, we need to cut off something at some scale. And the scale, because this operator, P to the R1 delta P to the N, is somehow something at time R2, and not R1, because N is R2 over R1. So it's at time R2. And all the mass of the heat kernel is then contained in a ball of radius something like R2. If you cut off with a ball of radius CR2 for some large C, you will not lose anything because the information is still in your smaller ball. So this expression, this P e to the R1 delta P to the N delta X, bounded above, and I introduce now the cutoffs. And the cutoffs, as I said, they don't make you lose anything really important. So the remainder is controlled. And now the idea is that here you have delta X, which is something very singular, not very good. You just take, here you have a power N, which is large. You just use one of the powers to apply it to delta X so that it's smoothed now, because you have a heat kernel here. And now you get, okay, it's not proved exactly on the slide, but you can imagine that it's upper bounded by the supremum over all phi of modulus 1. And there is a constant, of course, here. And this operator to the n-1 phi. And the beauty of this operation is that now you have something which is an eigenvalue by the Rayleigh quotient principle. Okay, you have an eigenvalue, and the eigenvalue by functional calculus, you can put the n-1 outside. And this is how you will get that your n here is getting out of the norm. And this is very important, as I said, because you have to make your gain bigger. So now you have a supremum, you consider an optimizer, phi x in the sup, and there remains to prove, because you can forget now there is a power n here, a power n here. So you can forget all the n's, and again now you are at scale R1. What you want to prove is that the fact that you introduce the p makes you have a 1 minus epsilon of g. And in fact, here it's still bad because you have an eigenvalue and you don't know how it's related to phi x. But the good point is that, again, by a good application of the min-max, you can prove that for most points x, this quantity is bounded above by mu2 to the R1. Somehow, it tells you that the eigenvalue in the surface controls the local Rayleigh quotient or something like this for most points. It's kind of clever, in fact, this thing. There is an analog in the graph case. We took inspiration from this. And, hence, now we just have to show that this is bounded above by this, and you see that it's better because you have phi x on both sides. You can just try to make a difference or something. And this is actually the last slide of the proof. So I just simplified by forgetting about the cutoffs because it was too complicated otherwise. And also, very importantly, I removed here there was a modulus, okay, an absolute value. I remove it for the moment, and you will see in the end why it's important, actually. So if I remove it, I just take the difference of the two terms. I'm trying to prove a lower bound, because you want to prove that you have a gain. guy with the piece is not too large. So this is where everything is it's the core of the proof now. So it's you can express it by some manipulations as identity minus p e to the r1 delta phi x square. So phi x, I just recall you, it's an eigenfunction living in the ball of radius CR2 around x. An eigenfunction of a complicated operator.
I have a question.
Yes.
Is it the first term only non-negative? The first difference?
The first term, yes, it will be non-negative because you see it's equal to this, which is a square.
Okay.
And by the Pythagorean theorem, since you have an orthogonal projection, this is where you use what is P. The orthogonal projection to the orthogonal of the space of all one characteristic functions of a VK. And VK were balls around the points of the net. And here you have this expression now. To the R1 delta phi x against 1 VK to the square. And you want a lower bound on this. So you just, it's a self-adjoint operator, you put e to the R1 delta on the other side. And now the idea is here, it's the one I mentioned a moment ago, that if you apply e to the R1 delta to the characteristic function, since you have a net which is well distributed on the surface, e to the R1 delta 1 VK, when you sum over k, you get to cover all the surface, in fact, because e to the R1 delta times the characteristic function is somehow something like a characteristic function of a ball of radius R1 around xk. And you are testing against phi x, and so all the mass of phi x will somehow be detected in this sum. And this is what I say here, since vk is the small ball around xk and the xk is from an R1 net, the functions here somehow cover the whole surface. It allows to prove a lower bound for this of order epsilon of g times this thing. And when you now you write it and you put it the right way, you exactly get in the end this inequality, this gain. So you see there is a clever geometric idea of putting a net and then using it with the heat kernel. However, I lied to you. It's that it turns out that phi x here, of course, you have a square. And so it's good if phi x is positive, because otherwise there could be some cancellations. And it turns out that phi x is not positive. It's both positive and negative values. And why? It's just because phi x is defined as an eigenvalue or as an eigenfunction of this operator. And this operator has no reason to be Frobenius, to satisfy the Perron-Frobenius theorem to have a top eigenvalue which is positive everywhere. It's not the case. And so actually, there is another game which is in fact quite a big part of the proof, where you use the fact that you have the right to put an absolute value to overcome the fact that you have a function which takes both positive and negative values. And finally, the last remark is that this proof, why does it also works for counting the number of eigenvalues in a small window and not only for exact multiplicity? So I need to go back a little bit in the slides. Here, at the beginning of the trace method, you see that it's quite flexible because the trace of this operator, if the eigenvalues are quite close to each other around mu2, somehow it's not far from being the same thing than m prime mu2 to the 2 and r1. You are not using that it's exactly equal to mu2. So this is why it's flexible somehow. And let me finish with the slide of conclusion. For the future goals, and I would say it's in fact common to different subjects. For hyperbolic surfaces, it would be interesting to develop techniques which allow to distinguish eigenvalues as close as 1 over log g. What I want to say by this is that, in fact, our method doesn't distinguish the eigenvalues when they are inside the small window, meaning our bounds are not better for exact multiplicity than for approximate multiplicity. And in fact, it's not the first time that this kind of problems occurs. For example, in the paper by Laura Monk, there is the same problem, and I'm sure it's in some other places. And in our case, one way would be to understand traces of the heat operator for t much larger than log g. we stopped at R2, and R2 is C log G, and there is a good reason for this. Because in fact, the typical diameter of M is of order log G. And in the same way, here I stated the problem for hyperbolic surfaces, but you can start with the case of graphs, and you can try to improve bounds on the exact multiplicity, and you have the same problem of understanding timescales greater than log G. So I thank you very much for your attention.
Thank you, Cyril, for your talk. So let's open the floor to question and comments. So if you have any question or comment, you can unmute yourself or you can put it in the chat.
Yes, I have a question. What estimate do you need for the heat kernel? So it's a large time heat kernel?
Yes, it's large time, and it's in fact what we are using strongly is that we are using the heat kernel on the universal cover.
Yeah.
Because we are first working. So there are two things to reduce to the. It's not difficult to handle the varying curvature case because there are some comparison of heat kernel estimates due to Berger, to Mazet, Gauduchon maybe. Okay, it's a paper in the late 70s, I believe. And then in the constant curvature case, you have to know you have to understand how for example, the heat kernel on H2, the hyperbolic plane, works. So it's not so difficult. Somehow you have to put all the remainders at the right places, but this is the heat kernels are not so difficult, I would say.
Okay. In particular, does this kind of estimates, does it work in any dimension if you have some pinching of the curvature? Because it seems that there is not many places in your argument which use the fact that the dimension is 2.
Well, I must say we didn't think really about higher dimension because I thought it was because of your results. It was not so interesting.
No, but okay.
But maybe, yeah, maybe.
My example are not this negative curvature.
Okay,
That's
good. I
different
should have
story.
talked before to you.
Okay, so but how to say that? Assume the sectional curvature is pinched between two negative constant A and B. Okay.
Yeah.
Assume the injectivity radius is smaller than your delta or something like that. Then maybe your proof can be extended to show some bound, not in terms of the genus, but in terms of integrals of some power of the curvature.
Okay.
Some polynomial or in terms of the volume, in fact.
Okay.
Because you have some pinching of the curvature. Okay, you replace the genus by the volume. That's very simple.
I understand. I understand.
And because otherwise the combinatorial part,
There is nothing special.
Doesn't see the dimension.
No.
Okay, so the main thing is the heat kernel estimate, I guess. No.
Yes.
Okay, so you have a comparison theorem in higher dimension for the heat kernels?
Yeah, I think so. Yeah.
It's for any dimension, no?
Yeah, I think so. That the same paper works. Yeah.
And for the hyperbolic space in any dimension, it's completely explicit. So it has nothing to do. I guess you should try.
Okay. Sure.
Sure.
So there is a question in the
I
chat.
ask a question.
Yeah, sure. Go ahead.
It occurs to me that if you have large multiplicities all spread around the spectrum, if you have a trace formula, it should show itself somehow in the distribution of lengths of periodic orbits of their spectrum, if you consider it as a spectrum. Is there anything known about this possibility, or is it known that in such systems that you described, there are certain distribution properties of the length of the periodic orbits.
You mean when you know that you have high multiplicity, you want to understand the length of the periodic orbits?
How does it affect the distribution of periodic orbits? If the trace formula is even approximately correct. Maybe it is not a question.
You are looking only at one eigenvalue.
I cannot hear
not
you.
All eigenvalues.
If I cannot hear you.
Okay, I can repeat. He is saying that we are looking at one eigenvalue and not I mean, with the multiplicity of one eigenvalue and not at the statistics of the spectrum. But
yeah, but you said that MJ, you have MJ, and the J is
so
you look at various J's.
Yeah, so for each J you have a different constancy, but
it is a multiplicity.
Yeah, of course. Yeah. So short answer is I don't know, and yeah, but that's interesting.
So there is a question in the chat which says that why you're looking for the multiplicity of first Laplace eigenvalue, if I understood the question.
So what is the motivation? Yeah, so it's not only the first. You can look at anyone, and the reason is so as I said, there were some works, for example, about also the multiplicities of representations, of irreducible representations. It is very related. This is the context in arithmetic, etc., that people were looking at. It's old papers by De George, Wallace, and in the context of quantum chaos, which is also in the audience, many people are great experts. I know that it's mentioned. Where I learned is in the book by Bergeron. There is some place where he says that multiplicity is related to quantum chaos. But if you know sufficiently good bounds on multiplicity, but our bounds definitely don't enter this picture. It's just the general idea of looking at multiplicity. I mean, it's natural. A spectral gap is related to mixing of random walks. Multiplicity is not physically so as clear, but I mean, natural in the sense of mathematics.
Yeah. Okay. Yeah. Thank you. So any other question or comment? Okay. So may I ask? Oh, there is another question. What about positive curvature?
So answer is I don't know, except that in positive curvature, the question of the genus is a bit different. I mean, of course, by the Gauss-Bonnet formula, it's not exactly the same kind of question that you would have because it's not. So answer is we don't say anything because we are using strongly universal covers and limit of high genus, but it's still an interesting question.
Yeah, and maybe I can ask one last quick question. So you highlighted the role of the lower bound for this pinching curvature when you bound the volume and also the injectivity reduce when you use the upper bound for the sectional curvature in the estimate for the heat.
Yeah, we use it in the estimate for the heat. So
yeah, basically my question is how this constant C in your main theorem behave when this upper bound goes to 0 or
no, this we can make explicit.
Okay.
This we can make explicit in terms of A and B for sure.
Okay.
We didn't do it, but it's explicit. Even in terms of rho, in fact. This is a thing we didn't do, but yes. Because what is very good, I can answer for rho, but what is very good is that you have some structure with the Collar lemma, which tells you that if your rho is too small at some place, then you know that you have a very long tube where you know roughly how the metric is. And so you roughly know how to pick your R-net inside. So if that's the answer for
Okay, thank you. So if there is no other question or comment, let's thank Cyril again for his nice talk.
Thank you very much.
Yeah, and thank you all for attending. And before we close the session, I want to announce that next week we have Michaela Ejidi, and she will talk about complex analysis, thick set, and the spectral inequalities. Thank you.